Well, hello and welcome to this exercise on circle theorem. And this time around, we're going to take in area scale factor. Sorry, we're going to take in the area of a sector as well. Now, this is certainly a A-style type question, and it actually borders on AS level year 12 mathematics. The only difference is that in year 12 you might be talking in terms of radians instead of degrees. That's the only difference. Anyway, just to paraphrase, we've got a circle with center at O there, and we've got radius OP and OR. We've also got enclosed in here is a sector S, and the sector is bounded by the radius OP, the minor arc P and R, and the radius OR as well. Now this arc subtends an angle of 146 degrees at the center. We've also got a tangent PQ and a tangent RQ. Now we are asked to find the area of this region in red, described as T. We want to find the area of T there. Okay, right. To begin with, we need to find the area of the circle, which we know is pi r squared. For that you get no marks at all because you're supposed to know that already. So the area of this circle is 25 pi. Okay, 5 times 5 is 25. And the area of this sector here is dependent on the amount of the value of the angle subtended at the center by the arc P and R, and that's 146 there. So the area of the sector is 146 divided by 360, 360 being the sum of the angles in a circle or at a point there. Okay, now multiply that by the area of the circle. That will give us the area of the sector S there. Now you can work it out now, or you can leave it as it is for now. I'm going to leave it as it is for now. Okay, right. Now if we look at the quadrilateral OPQR, now that's got OP and OR which are equal, and also the tangents PQ and RQ which are equal, because if two tangents, from circle theorem, if two tangents meet at a point, then both tangents are equal. That's what we've got there. So we've now got a quadrilateral defined by OPQRS. Now because OP is equal to OR and PQ is equal to RQ, it seems to me that we then have a kite with a line of symmetry OQ there. Now that being the case, it means that the triangle OPQ and the triangle ORQ are congruent, so this triangle OPQ would be half of the quadrilateral there. Okay, moving on from that, so if you find the area of the triangle OPQ, that will be a half OP times PQ. Okay, but the problem is we don't know, we have no idea what the value of PQ is. We don't know what PQ is. We're not given that. So we now have to rely on a trig function, because PQ divided by OP will give us the tangent of 73 degrees. So which that means that PQ is equal to OP times tan 73 degrees. So this area OPQ now becomes a half times 5 times PQ. Now PQ is now OP times OP times tan 73 degrees there. Okay, and OP is 5. Okay, right. Now the area of the quadrilateral is, the area of the triangle is half the area of the quadrilateral, or if you like, the area of the quadrilateral is double the area of the triangle. Okay, it doesn't matter which way around you put it. So what we've now got is that the area of the quadrilateral is twice the area of the circle. It's half times 5 times 5 times tan 73 degrees there. Now the 2's will cancel out, so we end up that the area of the quadrilateral is 25 times 3.27, because 25 times the tan of 73 degrees, it gives us this one here then. Okay, now to find the area of T, what we then do is we subtract the area of the sector from the area of the whole quadrilateral there. So the area of the quadrilateral minus the area of the sector S would then be 25 times 3.27 minus 25 times 1.22. If we now isolate 25, we have that 25 into 3.27 minus 1.22 will give us something like 25 times 2.05 centimeters squared, and that gives us a figure of 51.25 centimeters squared. And to the nearest integer, the answer will be 51 centimeters squared. And I hope all that made some sense. Please subscribe. Thank you for watching, and bye bye.